one as we continue on in our curriculum, which is titled Angles of Triangles. So let's go ahead and get started. First of all, we're talking about classifying triangles. Triangles, of course, the word triangle, three angles. So it's the polygon with three angles and three sides. We classify these guys. First of all, we're going to consider classifying it by angle. So considering what types of angles we have within the triangle. First type of triangle we're going to discuss is the acute triangle. And of course the acute triangle, discussing the three angles within the triangle, what's their nature. And in this case, the acute triangle has all three angles are being acute. The next that we'll consider is the obtuse triangle. The obtuse triangle has one obtuse angle. Remember, obtuse angles have greater than a 90-degree measure. So it's impossible for us to actually have a second one, right? Because if we're going to try to have that, there's no way to connect that third side, right? You just create an obtuse angle. So one will be obtuse, and then the other two are going to be acute. Last but not least, we have the right triangle, which there's going to be exactly one right angle, and then there are going to be two acute angles. It has to be by definition. Next, we're going to consider classifying these guys by side. Okay. First is the scaling. And again, this is a 7th grade standard. This is something you probably have heard of from middle school. If not, it's okay. You just need to make sure you review these terms. But a scaling triangle is a triangle where we have no sides that are congruent. Next, we have the isosceles triangle. The isosceles triangle, because we have to think about what our options are. So we can either have with our three sides, they'll all be unique, right? So one will be congruent to itself in all three cases. In the case of the isosceles, it's not that there are two sides, and this is a common misnomer. It's not that we have at least two sides that are congruent. So people think, okay, well, if it's at least two, that means two or three. Those are your only two options. And then the last type we have is the equilateral triangle, which is also equiangular. Equal lateral sides, so equal sides, and equiangular, equal angles. So if all the angles are congruent, then all the sides are congruent, and if all the sides are congruent, then all the angles are congruent. And going back to the isosceles, what it would mean is that is an equilateral triangle also an isosceles triangle? And the answer is yes. And as we continue through the course, these properties for an equilateral triangle will, the properties of an isosceles triangle will apply with regards to some of the theorems to equilateral triangles. So just something to keep in mind. Right, so continuing on. Actually, just review, it's kind of like, in this case, it's kind of like the notion of rectangles and squares, right? A square is a specific type of rectangle. A square is a rectangle, but not all rectangles are squares, obviously. So let's go ahead and take a look at a problem we'd have, right? And classifying one of these guys. So we're going to draw a triangle in the coordinate plane. So here are our coordinates. The 3 points that we're going to have that will make up the vertices of our triangle. The first one being point A, which is 0, 3. The next point, which is B, which is 7, 2, 3, 4, 5, 6, 7, 1. And then C, which is 1, -1, okay? So we're going to go ahead and connect the dots here, these three guys, okay? So our directions here that we are going to classify, let's make sure this guy gets done a little bit clearer here, classify triangle. Now, we don't have to write the word triangle. Notation-wise, in mathematics, they use a little tiny triangle next to the word ABC. It's nice, so we don't have to write that word anymore. We have a shortcut, which we love shortcuts. Okay, so how are we going to do this? Well, if we're going to classify it by side, it means that we need to find the length, or, of course, I think you maybe see it coming, we need to find the distance in this coordinate plane. It's the only deductive way that we're formulaically going to be able to prove the exact distance of each segment that makes up a side. So I need to find the distances of all three sides. AB is one of the sides, BC is a segment that makes up another side, and AC, of course, a segment that makes up another side. So we're going to apply that distance formula. So going ahead with AB, so the big square root sign. So we're going to take the difference of the x's, so we have 0 minus 7 squared, plus 3 minus 1 squared, right? The difference of the y's, which of course 0 minus 7 is negative 7 squared, plus 3 minus 1 is 2 squared, and of course there's 49 plus 4, which is equal to rad 53. BC is going to be difference of our x's, 7 minus 1 squared, plus 1 minus minus 1 squared. Okay, 7 minus 1 is 6 squared, plus 1 minus minus, which is 1 plus 1 is 2 squared. So that gives us 36 plus 4, which is going to be rad 40. Now, rad 40 can be simplified, but I'm not going to in this case. It's actually additional work. Because in the end, remember, what we're trying to see, if we're classifying by side, is how many sides match? How many of the calculations are going to match? So right now, rad 53 and rad 40 don't match. We could make rad 40 to rad 10, but there's no reason to apply that right now, right? Just going to create a little bit of additional confusion. You're going to see once we get through AC. So AC, of course, we're going to have difference of our x's, 0 minus 1 squared, plus, and of course you can do 1 minus 0. The result's going to be the same, right? 1 squared and negative 1 squared, it's the same result, right? So that's how the distance formula, one of the ways it's actually kind of a forgiving calculation. 3 minus minus, right? So it's plus 1 squared. So we have negative 1 squared plus 4 squared, which of course is 1 plus 16, or ultimately rad 17. So how many of these match? Well, we have 3 different radicals. Even if I made it to rad 5, if the thing is if it's just additional work, right? Or excuse me, 2 rad 10 for rad 40. It's just additional work that ultimately isn't going to pay any great dividends. Right now, we can verify in its current form whether or not any of these match. So what we see is that they don't. So of course, the type of triangle classified by side, where all sides are different, is the scaling triangle. So that ultimately is your answer. Now, if you do this on a test and you just guessed, you just gave me one of those answers, scaling, isosceles or equilateral, I wouldn't give you any points because it's just purely a guess. The idea here is that you're trying to deductively prove what it is. So we need to do that calculation. Next is the notion, which is a theorem many of you have heard before, which is the sum of the interior angles of a triangle is 180 degrees. And I don't know if you really have seen sufficient deductive proof as to why that is the case. Many of you have just heard this, right? Sometimes it's like, well, if you take a square and the sum of the interior angles is 360 and you could chop that in half, you have 2 triangles, so it's 180 plus 180. That's cute and that kind of works, but it's not really a deductive proof. Because first of all, the premise that's based off of is that the sum of the interior angles of a quadrilateral, and moreover for a square, is 360 degrees. And what proves that? So let's actually go ahead and first prove this just on its own. So we're going to go ahead and just take a triangle, right? We're going to call this triangle ABC. In triangle ABC, I can construct what's called an auxiliary line here. So through any of the vertices of the triangle, I can construct a line that is going to be parallel to a side opposite. So for example, here, right? That line, I know it's kind of a crooked line, but right, the idea is that it's going to be parallel to BC. Or I could draw a line through B, right? That's going to be parallel through AC, or through C, parallel to AB. So the idea is that I only have to prove one of these cases. Okay, and that's what we're going to do here. I don't need to do 3 cases. I'm going to prove, right? So this guy is going to be, we're going to call this guy XY. Okay, let's make our vertices a little bit more pronounced here, but with points. We're going to go ahead and just do a proof. So what we're given here, first of all, is our triangle, and we also constructed that auxiliary line. So the given is that we have triangle ABC. Remember, we use the little mini triangle because why would we write the word, right? It's too much work. ABC. with xy parallel to BC, and we're going to prove that the sum of angle C, and of course we can say angle C, it's not ambiguous, right? There's no other angle that this guy could be, okay? We're going to say that C, and we want the sum of all those interior angles, so C and B, and the other angle, if I said angle A, that's ambiguous, right? Because angle A could be this angle right here, right? XAB. That could be angle A, right? Or it could be this guy right here, right? It could be a number of things. So we're going to number these guys 1, 2, and 3, okay? And again, our given is that we constructed XY and BC parallel. And we're going to say that this is angle 2. And we're going to say that the sum of those we want to prove is 180 degrees. And when we do that, we've actually proven the interior angle sum for triangles. So let's go ahead and do our proof, our 2-column proof, right? So of course, we're going to start this guy. Statements on the left, and the reasons on the right. For the first one, of course, it's triangle ABC with XY and BC being parallel as our given. And next, one of the things that we're going to show is that, I don't know if you've ever seen this proof before, is that if we were to tear off all of the angles of a triangle, it's not really a proof. It's go make a triangle out of paper, tear off all the corners, right? Tear off all the angles, and if you set them with all the sides being adjacent, it's going to create a straight line on the bottom end of it, or on the top end of it, right? So on one end, which is an 180 degree, right, straight line, that straight angle 180 degrees. So it's not really a proof because you're just cutting paper. But here we know that that this is going to be effectively an 180 degree angle. And sometimes people say, well, all three are supplementary to each other. That's not the case, right? You can't have 3 supplementary angles. Supplementary angles are a pair of angles. So let's take a pair we know are supplementary. In this case, we know that angle 1, right? And then angle 1 is going to be supplementary with this guy right here, which is angle CAY. And the reason they're supplementary is because these guys are a linear pair. Now, supplementary angles, we know by definition, have a sum of 180. So we can say that angle 1 plus angle CAY is equal to 180 degrees, right? And that's our definition of a supplementary angle. Or supplementary angles, moreover. So now that we know those are supplementary, well, within CAY, right, it's constructed, because remember, we said 1 plus 2 plus 3, but we can't just say, oh, for whatever reason we like they're equal to 180, because there's no distinctive rationale that we use, right? We can only use on that right-hand side under reasons, definitions, properties, postulates, and theorems. The issue is that we don't have any of those that would say that 1, 2, and 3 are indeed supplementary. Okay, so that's what we're trying to get to, but we know that that angle right there, CAY, is constructed of angles 2 and 3. Remember, when you use 2 angles, put them together to create a bigger angle, that technically is one of our postulates, which is the angle addition postulate. Okay. So, that's good. But if we know 1 plus CAY is 180, and we know 2 plus 3 is CAY, then again, now what we were trying to get to is we can say sufficiently that 1 plus 2 plus 3 is equal to 180, right? And, I'd actually take the substitution property, but this one is technically transitive, right? A plus B is equal to B plus C, then if A is equal to B and B is equal to C, then A is equal to C, right? So effectively, what we're replacing CAY with is 2 plus 3, up in that above step 3 right there. So ultimately, it's transitive. Where we're going to actually see substitution is in the next thing, because what we're trying to prove is this right here, right? Well, remember, think about what else you know that angle 1, what it would actually be equal to. In this case, angle 1 would be congruent to angle C, as it turns out, because that's what we're trying to show. We don't really care so much about this. We're trying to transfer the notion of these angles being supplementary is going to apply to this triangle. Well, 1 and C are congruent, as well as 3 and B. And I hope you saw that from the get-go. And if not, you're seeing it now. When we do these proofs, one of there's a few popular methods I think you'll see through the course. One is anytime you see vertical angles constructed in a diagram, that's going to create congruence, and you're going to utilize that. We don't have anything vertical here. But something that's going to cause congruence that's not going to be immediately adjacent is this notion we have two parallels cut by transversals. These are alternate interior angles. So we can use that theorem, right? When we have two parallel lines cut by a transversal, the alternate interior angles are congruent. So those are alternate interiors. 1 and C are congruent, which is nice because now we're getting closer to our answer. Because what we can do is instead of 1, we can say angle C plus angle 2. Instead of 3, we can say angle B. And that's all equal to 180. And that right there is substitution. Now, gentlemen, this and this do not match. They just don't. They don't exactly match. They're very close. But we know through mathematical properties, we could actually flip some things around and now make it C plus B plus 2. And that's the idea. Is our last step should exactly match what we have under proof. And we can flip around angle 2 plus B and B plus angle 2 because of the commutative property. Right? The commutative property of addition makes it where you can flip these things around. So guys, there we go. Now we know deductively that the sum of the interior angles of a triangle are indeed 180. Next, we have another theorem, and I'll talk my way through it just to kind of show you what's going on, but this is going to be a proof you're going to have to do in one of the homework problems. So construct this diagram, and what we're going to do here is what's called the exterior angle theorem. In the exterior angle theorem, let's actually identify some of these parts. So angle 1 is that exterior angle that we're referring to. Okay, and not only are angles 2 and 3 interior, but they're actually what are called the remote interior angles. Think about what you would need the remote control for the TV. The remote is used to change channels across the room, right? The remote operates the TV across the room. So that's the thing, is that these guys are across, they're away from angle 1 versus this unnamed angle right here, which is just merely adjacent, okay? So what this says is that the exterior angle, which is 1, is going to be equal to the sum of the remote interior angles. So 1 is going to be equal to 2 plus 3, okay? The way we justify this, and the way I'll just explain the proof for this, is that right here we have two angles that are supplementary, therefore have a sum of 180, because they are a linear pair, okay? Now, we have this guy, right? Which is unknown, plus 2 plus 3, which we just proved the sum of those three angles is 180, right? So if that's the case, then these two, and then the sum of the interior angles are going to be equal to each other. Then you're going to subtract off that unnamed angle, leaving you with 1 is equal to 2 plus 3. So, just kind of talk through that quickly. See if you can actually assemble that logic in a 2-column proof. So let's go ahead and solve a problem utilizing this logic. So I'm always entertained by people say, oh yeah, this diagram is upside down, and again, we're trying to divorce ourselves from a strict orientation of things. Who's to say what's right side up and what's upside down? If I had drawn the example this way, your notion of what's upside down, right side up would be flipped. So it doesn't really matter. It's just the same exact scenario though, right? And in here, I have angle PQS, which is 3x plus 25 degrees. And I have angle R here, which is 2x degrees. And I have angle S, which is exactly 65 degrees. And what we're going to try to find is the measure of angle PQS. Now, this guy's fairly straightforward, right? Because again, that remote exterior, 3x plus 25, is going to be equal to the sum of the remote interiors, right? So it's going to be 2x plus 65. Okay? This guy is going to be equal to the sum of those two. That's what we just discussed. So let's go ahead and solve, right? Minus 2x, minus 2x. These guys cancel, so we have x plus 25 is equal to 65, minus 25, minus 25, right? So then we have x is equal to 65 minus 25, which is, of course, 40. So we're going to take that. We didn't actually solve the problem because it wants PQS. So the measure of angle PQS is equal to 3 times x, which we just found out is 40, plus 25. So the answer here is actually 145 degrees. Okay. Last but not least, last problem for today is that we're going to say that the measure of one acute angle of a right triangle is 1.5 times the measure of the other acute angle. We're going to find the measure of each acute angle in this case. Okay, so corollary here. We haven't discussed any corollaries yet. So corollaries are awesome. They're actually another thing that we can utilize as sufficient reasoning. It's on that right side of the two-column proof, right? We can fill in definitions, properties, postulates, and theorems. So postulates and theorems are kind of new to us in this course so far. Corollaries are directly related, right? What a corollary is it's a statement taken as a simple truth. Some of you guys are thinking, hold on, that's a postulate. But the way we take it a simple truth from is from a theorem. Oh, so it's kind of like the postulate of a theorem, right? But we wouldn't say that. Instead, we say it's a corollary. We're going to encounter just a handful of these. They're not really going to often be used in our course, just in our problem solving as reasoning within our proofs. But it's very common reasoning we're going to use mathematically, and even just outside of this, you're going to find discussing various ideas. So here's our corollary here. So we have this right triangle A, B, C, okay? Well, we already should know what the sums of angle B and C are, right? Because the sum of the interior angles have to be 180 degrees for an entire triangle. Well, this guy already takes up 90 of those degrees. So the other half, the other 90 degrees have to be split between B and C. What does that mean? Well, it means that these guys are going to be complementary. We don't really need a proof to do that. It's kind of a quick thing that you can just take away and just know that anytime we have a right triangle, those two acutes are going to be equal to 90 degrees in their sum. So that's how we're going to do this. We have the two acute angles of a right triangle. One of them is 1.5 times the other one. So the sum of those two, of course, is going to be 90. So 1.5x, right, times the other guy is going to be 90. So in other words, this guy's 2.5x is 90. And, without a calculator, let's actually just use fractions, right? 5 halves is the same thing as 2.5. And then here, I can just multiply by 2/5 on both sides, so I can get x by itself on the left. And again, I can factor out the 18 out of the 90. 5 divided by 5 is 1, so 18 times 2 is going to be 36. So this is one of my angles, right? And then to find the other one, I got to plug it back in. So 1.5 times 36, which we know is actually, 1.5 is really 3 halves times 36. And then we can just factor here. And 3 times 18 is 54. Now, again, what we could have done is once we solve for one of them being 36 degrees, you just know that if they're complementary, the difference between 90 and 36 is 54. So you just do 90 minus 36. Go ahead and start your homework here. If you have any questions, of course, you can contact me. Good luck.